My talk is about how collaborations know, basically. How can it produce knowledge? It means to me, how it knows. Because if one person measures something, you apply your ruler, you see the numbers, you measure. Or you infer an equation, you know. That's how you know. But how 100 people can know one thing? How recently, actually yesterday, I read of a collaboration of 5,000 people who published one paper, more than 5,000 people.
In the author list.
Yes, author list. How they know? Who of them knows what? Actually, that's the interesting question. Yes. Because
yes, maybe nobody knows everything.
Yes, maybe no. Yes, that's not one of the options. So, in a sense, I'm standing on the shoulders of giants of thought. Not everything I will be talking about are my inventions and discoveries in philosophy. It's mostly compilations, but also some my arguments. So, the outline of my talk: what is collaboration in HEP, especially? It's some of its structure, and what is the result of collaboration's work? Well, to obtain results, we need to aggregate somehow results from hundreds and thousands of people. How to aggregate? Different types of aggregation in small groups and large groups, and interdisciplinary groups like physicists, biologists, and so on, or same type collaborations, models of aggregation. And when we aggregate, we somehow involve certain values. That's about values. Yes, that's what you talk about.
Values are everywhere.
Yes, values. That's about values, because we do need somehow to ascribe certain weights to results of each of thousands of people. So that's about what we need to do. Is science value free? And certain people argue that it is not value free.
Of course.
Yes. There are arguments like inductive risk, for example. And after that, this first part is sort of theory. Then I will consider a case study, short case study of a recent discovery and undiscovery of superluminal neutrinos. Neutrinos that were claimed to travel faster than light, and soon undiscovered. And I will shortly analyze this case. Are the deliberations and dissent in collaborations important or not? Is it possible or not in a big group? Why is equality or justice a legitimate value for knowledge production and collaboration? And is CBPR, so-called community-based participatory research, a solution here? This philosophers recently started to discuss this concept of community-based participatory research, how to involve community, at large members of community to research.
Community, it means scientific community?
That I will be discussing. They mean not only scientific community, just
public.
Just general public, yes. But there are features. So, and summarize. So, what is the structure of collaboration? People who consider collaborations claim that collaboration is a research group. Basically, they distinguish between research group, and a scientific community as two distinct sizes and two distinct options. But I argue that collaboration is not a research group by itself. Group is 3-5 people who work immediately with each other on a daily basis. That's one thing. And collaboration is generally composed of tens or more number of groups, research groups. And certain people can participate in work of several groups, but not at the same time, not simultaneously, basically. Because collaboration is a more complex form than a research group.
Big
It is-
collaboration. You mean
Yes,
some
big collaboration is, in a sense, is a model of a community, a small community. So it is in possession of certain features of a group, but also certain features of community at large. So, and Peter Garrison distinguished three types of people working in the big experiments: there's theorists, experimentalists, and instrumentalists. That's 1980s.
No,
So
no
that's-
managers.
Yes, no. So okay, we'll get to this. So basically, what I think about this, we can distinguish at least four stages of the experiment: design of an apparatus, preparation of phenomena. You need to hit a target with your beam or some prepare events. Then you need to measure events, measure phenomena in a detector, and after that collect data, and after that to analyze data or aggregate results. So four distinct stages of the activity, the entire activity. Basically, experimentalists are those who participate or took part at all four stages. They participate in design, they participate in preparations and measurements, and data analysis. Basically, it is associated with data analysis, because data analysis eventually brings you results, what you can publish, and so on and so forth. So, but it includes not only that. I think that instrumentalists are those who participate in design and preparation of phenomena, but do not go further.
But what about the very idea of experiment? It is in design or where? Or it is even before? The first idea of experiment.
Experiment is preparation of phenomena and measurement of them.
Mm-hmm.
Prepare and measure. To prepare something, you need to design your apparatus.
Yes, but
And
before you should have an idea of this experiment.
Yes, absolutely.
So it's outside this.
Yes, that's about activity,
Okay.
roles.
Mhm.
This idea can be brought by theories. I'll talk
So
shortly
it is
about that.
outside.
Yes,
Make sure. Okay.
but it basically, in sort of an ideal case, theories propose experiment. They propose what the people should measure, and people think how to measure, what to build, what to hit with what beam, and so on. Just I will give you an example. So, and what happens is in a large group is the division of epistemic labor, of knowledge production labor. And in a sense, as people argue, it can be called epistemic dependence. So people in a group depend on each other's knowledge. So there can be group view of the entire collaboration, which is not reduced to individual views. And also there are beliefs and acceptances. You can believe some laws of nature. Okay, this is an interesting question. Basically, acceptance involves voluntary action. So you need to decide, I will accept this. But belief doesn't require it. You just believe something. But actually, for science, many people maybe they already don't remember that E equals to mc square, for example. Yes, they don't remember how to infer this. Why is it so? They just believe that as something the very basic. So that's a sort of belief. But otherwise, we need to accept, well, for example, if you tell me that your accelerator beam is 100 or 1000 GeV or 1 TeV, say the TeV beam diametron, You are an accelerator specialist. Tell me, and if I'm a particle physicist, I need to accept this, to believe you. I can somehow calibrate your authority, as Philip Kitcher calls it, so I can assess your professionality in a certain way, or listen to experts and, who can assess your specialism.
Always thinking about how to check it.
How
We
to
are
check,
always,
yes.
we do not believe just belief and that's all. We always thinking how to check one or another point.
Yes and no. Yes, because we try to apply sort of logical reasoning, consistency check, and so on. But on the other hand, particle physicist, if he is narrowly specialized particle physicist, cannot assess accelerator physicist. He needs to believe, to accept somehow.
To believe and also always to be open for idea to check.
Yes, yes.
This is always.
Always.
We cannot check everything, but we
Because,
should be open.
yeah, epistemic vigilance. You also need to suspect that you
Yes.
may be wrong and
Exactly.
try to figure out how to check it.
Mhm.
Okay, so this requires trust. And sometimes it requires testimony. You can need to provide me the number.
But
Okay,
this is another sort of trust which I may, for instance, trust to my friend. When I'm trusting to my friend, I am not supposed to think every day how to check actually him. Maybe he is lying to me. It's different thing. But in science, in scientific research, although I trust you, but also in my mind, I'm also thinking, I should think how to check one or another your statement. So this is different sort of belief and trust than we have in ethical sense when I trust my friend or somebody trusts his wife.
yes, exactly. People distinguish between moral, trust in moral character, and trust in epistemic character. It can be
Different sort
bad
of
guy, but good scientist, and vice versa.
This could mislead, by the way, and some people are misled.
Yeah.
So we believe in Maxwell equation. No, we using Maxwell equation, but we do not have that sort of belief in Max or in standard model or in calculus or whatever. We are always open to check this. It's different sort of acceptance.
Yes, but because of very high specialism, sometimes it's not possible to check consistency of something. You need to believe
Yes,
something.
yes, but it is good idea in science to try to find out how we may check it. But it would not be a good idea, for instance, in family life, to think how I may check my wife. Maybe she is cheating me. If I feel think every day, I don't think it's healthy. Huh? But in science, it is healthy. So this is the difference.
Yeah. Okay. So that's about the knowledge structure. So, and how to aggregate data. Basically, to my view, interdisciplinary collaboration, like collaboration between biologists and physicists, for example, in a certain sense, close to what people do in high energy physics, because the difference between biology and physics sometimes is as large as the difference between accelerator physics and particle physics. There's just very narrow specialism in this. So there's a sort of interdisciplinary research as well, even in high energy physics. How do people aggregate? In the simplest case, if scientist A knows that P and scientist B knows that Q, for example, you know that the beam energy is 1 TeV, and I see a peak in detector at 175 GeV, and I want to believe that I measure the top quark. But I need to rely or to believe that the top quark is produced by the right accelerator beam in a time window during the collision time and so on. That's what you provide me. You know that P about accelerator, I know that Q about the peak in the detector. And then we do AND in the simplest way, conjunction of this. So that's the simplest aggregation. And in a sense, I know that Q from my research, and I need to believe you that P. And then we know that Q and P, right peak and right beam. The B can do the same. You can do the same. And C can be the aggregator or a manager who can just believe me that P, believe you that Q, and then make a conjunction. Be an aggregator. And is it only trust that's necessary? Some philosophers, like Collins, for example, they describe very interesting phenomena. Sociologists working closely many years with physicists, astrophysicists, acquire, how he called it, interactional expertise. So they can answer physics questions, sociologists can answer physics question indistinguishably from a physicist. I saw it in a book, so at first I didn't believe that, maybe just a coincidence, but I saw in the book the question and the answer. And I am not an astrophysicist. I don't know a great deal in astrophysics. But to me, both answers sound very close. I couldn't figure out who is the sociologist answering astrophysics question.
Is the assumption that the sociologist doesn't understand what he's answering, and it's just answering
That's
from memory?
that's an interesting question, whether he understands. But it's about expertise. We need to distinguish competency and expertise. Expertise is the ability to communicate, to answer expert questions, to advise, and so on. But competent people understand. Not all experts really understand what they're speaking about. And not all competent people do expert work. So they don't speak out, they just work sometimes. So that's about that. So, but there is such sort of expertise. And what is necessary also for a collaboration work is a dissent in the collaboration. How it can work? If, for example, I know that P and you know that Q, but it is not Q. For example, you tell me, you believe that the beam energy is 1 TeV and it's only half TeV. You are mistaken with some kind of. And if I know only that P and you know that Q while it is not Q, aggregator C makes a mistake because you are a weak chain. One weak chain makes the failure to the entire argument, to the entire thing. What is dissent? Dissent is disagreement, possibility to disagree between collaborators, but to disagree with you that Q, I need also to know something about Q. Otherwise, I just believe this guy. I will show in my case study that that's exactly what happened. When one person knows only one part of the entire thing.
So there is no redundancy. We need redundancy.
Sort of. And so that's why dissent is very important. But for dissent, you need expertise in many areas. Otherwise, if you're only expert in one area, you don't know how to judge other people. Okay, so, and in a large collaboration, but for example, there is an outstanding a book by Ken Staley, who was intern student here many years ago. After that, he became a philosopher. He's a philosopher, and he has written a book, Discovery of Top Quark, about Fermilab.
Staley.
Ken Staley.
Staley.
He is a professor at St. Louis University. So, and he emphasized, considering this top quark discovery, he emphasized how difficult it is to organize deliberations in a large group, in a large collaboration. If you have 5,000 or they had 200 people, even 200 people, you cannot place them all around a table and debate. It will be endless, probably. So You need somehow, aggregator needs to suppress dissent, in a sense. So, and the special role, aggregator plays a special role in a large collaboration, a large experiment. A knows that P1, B knows that P2, and 100 people know that P100. But very few of them know about another P. Or if A knows that P1 and P2 and P3, he doesn't know P4 and P5 and so on. So many, so much of specialism here. And in this case, there is a special role of aggregator. Aggregator needs to be not only a specialist in P1 or P2, he needs to be a sort of interactional expert in each of the areas. And he needs to analyze data and aggregate the results. So, and how is it possible to organize the aggregation? First of all, one model, you need to suppress any dissent. Just your opinion is not important. You just give me P or Q or whatever, give me your number, and go home. And the aggregate. For this I need sort of international expertise. I know something about accelerator, in basic consistency, check basic approaches, and just to check your general consistency. And but in a small group, in the old experiments of the past, which I participated even years ago, were a group composed of sort of 5 people. It's much easier to organize the deliberations. You can sit all around the table and discuss everything. Is one, and second, there is no much specialism because each of people know each other's stuff, basically. Because they work together, they always discuss together, they substitute each other on shifts and help each other on work. So that's all more or less the same knowledge in small groups. But in the large groups, as it is Alan Franklin wrote in his book Shifting Standards recently, it's interesting that in large collaboration, aggregators are a group, only group of 5 to 20 people, in 100 or 1,000 people collaboration. 5 or 100 people have access to data analysis, to aggregate data. So that's how this aggregation is organized. Okay, so, but do we need or can we avoid value judgments during this aggregation? Basically, it seems that not, because first who talked about, in philosophy of science, who talked about values in science was Thomas Kuhn. He distinguished a number of 5 probably epistemic or knowledge-related values, knowledge-related, such as simplicity, self-consistence, plausibility, compatibility, mainly for theories. So, but recently, philosophers already argued that scientific rationality should integrate the ethical and epistemic values, to integrate ethical values to knowledge production. Why? First of all, let's consider Thomas Kuhn's values.
Are they considered ethical values?
Kuhn not,
No.
but currently yes. Epistemic values are several. For example, simplicity and compatibility with other theories. But if you consider any particular claim, scientific claim, it can be, if it's very simple, it's not compatible with others. If it is very compatible, it's not simple. So there is a trade-off between two values. But this trade-off is not epistemic, not knowledge related. if simplicity and compatibility are knowledge related, but when you're weighting them to arrive to this trade-off result, you need to negotiate this and that. So that's about why. And second, there is an argument of inductive risk. Inductive risk is, making judgment of scientific result always involves a sort of uncertainty. There is always uncertainty to claim that you discovered. There are two possible errors. You can reject the hypothesis which is correct on one side, and on the other hand, you can dismiss a hypothesis which is true. This is twofold thing. And always making a claim, discovery claim, is a risk. And that's what people call inductive risk. For example, in his recent book, Shifting Standards in Particle Physics in 20th century, Alan Franklin discusses the question of how many sigma you need to discover. How many sigma is sufficient to claim that you have discovered something in experiment? Why is it so important? When I, many years ago, worked in a small group, we never cared for how many sigmas. We just made the tables. These numbers are 2 sigma, these are 3 sigma, these are 4 sigma, and published this. There was no any essential risk because we didn't do any claim. We measured with this precision, and that's it. That was not a high stakes science. It was just normal science. But when people work in a science of high stakes, high costs, and high fame,
High public values.
it is always very risky to claim that you have discovered. And there is always a negotiation, how many sigma you need to, whether it's evidence or discovery or whatever. That's risk. That's about risk. And risk involves resolution of this risky situation, involves non-epistemic.
I was in CERN when they, time of Higgs boson discovery. It was public, one of the top matter of discussion, how many sigmas of Higgs boson should be achieved before the director of CERN would be able to pronounce that Higgs boson is discovered.
Exactly.
Is 4 sigma enough? Maybe 4.5. Everybody was involved. 4 or 4.5.
Yes, exactly. And that's what Alan Franklin's book is about. And you know that Fermilab invites Alan Franklin for a colloquium. He will be giving a colloquium talk here on 15th of July. So that will be excellent. I would recommend everyone interested in this sigma issue and then many other statistical issues and judgments in science to attend this excellent seminar.
So was it Corny or is it Franklin that brought the non-epistemic values into science, or is it both of them?
No. Kuhn talked only about epistemic values. He considered only epistemic values. But since more or less recently, people started to argue about that the non-epistemic, like ethical values, are also legitimate, can play a legitimate role. And I will argue that such values play also, while they are non-epistemic, they play also epistemic role. So let's consider very shortly, this case study about neutrinos traveling faster than light. In 2011, a collaboration opera at CERN claimed that the following thing. This anomaly, they measured speed of neutrinos traveling from CERN to Gran Sasso laboratory. They claimed that this anomaly corresponds to a relative difference of mu neutrino velocity with respect to the speed of light. So it is by 60 nanoseconds faster than light on this 500-mile distance. And it is my estimation that this result corresponds to 4 sigma. And 4 sigma, for example, for top quark discovery, 4 sigma was evidence, sort of evidence claim. In last decade, it was a standard that 4 sigma is like evidence and 5 sigma discovery. So it's sort of evidence of something. But before that, shortly before that, 2 theorists, Amosov and Volkov, published a paper about how to probe extra dimensions with neutrinos. There was a sort of a speculative work. It was a work about how to probe extra dimensions, measuring speed of neutrinos. They directly suggested to the experiment that CERN has the unique opportunity of measuring the indicated effects of difference, neutrino acceleration through these extra dimensions. And shortly after that, experiment opera claimed that they see that.
So according to these guys, Amosov and Volkov, neutrino should travel faster than light?
Yes, but that was against the Einstein theory, but it was not sort of a beautiful mathematical theory. That was sort of speculation. There can be extra dimensions. Everything can disappear to extra dimensions and appear from extra dimensions. Why not neutrinos, for example? So that's more complicated, but sort of this. That was not a theory competitive with Einstein. Nevertheless, it was influencing of some sort. And the collaboration who published this was composed of 174 authors. Here is the article in New York Times about them. So, according to Dr. Autiero team, neutrinos emanating from particle accelerator about 60 nanoseconds faster than it would take a light beam. So, and they claim that we cannot explain the observed effect in terms of systematic uncertainties. There was a claim in September 2011, but already in February 2012, the same New York Times published the following thing. In a detailed scrutiny of the experiment CERN in France, we found 2 problems. One is an electronic component that marked the exact times of GPS measurement. There was an issue with GPS measurements. And second, the circuit receiving the data introduced delay up to 60 billionths of a second. So that's the electronic circuit issue. Two issues were fixed, and this difference between speed of light and neutrino speed disappeared. Okay, so, but when people started to research what's going on, but because if you claim, for example, if you measure something faster than light and tell it to me, for example, I tell such things every day. But when you claim it in New York Times, there's something, all the world knows, they discovered something, then, they undiscovered something. So that's what's going on. This 174 people claimed the thing which was simply...
The joke at the time was, it's actually Italy, what is a fabulous country. Even neutrinos are flying faster than light there.
Well, I'm not about that. But I think those 2 theoretical guys were guilty in first place.
Yeah.
But but people figured out the following stuff. Data analysis and cross checks were performed by one person. By one person out of 174 authors. Second, other collaboration members didn't have access even to data.
High secrecy.
So that's one person play.
It's because of secrecy then?
Because because of high stakes.
Secrecy is a consequence of high stakes.
And basically, and also part of the person who analyzed data was responsible for this GPS stuff. He measured it out of 200 people. He measured a wrong thing. He analyzed it, the wrong thing. And he gave the interview to New York Times. So in published the paper. The question was how it works at all. Is it a collaboration? Do they know this or they accept this? Let's recall that the good aggregator needs to suppress dissent, suppress any deliberations, and aggregate data himself. So that's what was going on. And questions, basically, and also some philosophers, I recently read, interesting longitudinal study of physicists and biologists group, small group. They claim that people of different specialities, when they are not sure in each other's results, to increase confidence in each other's results, they engage each other in a question-answer dialogue and so-called explanative responsiveness. So I try to ask you questions, and you need to explain me, not only answer questions, but provide also logical reasons for me to believe you of different specialties. But when we look at this case, exactly what we see, that this person who analyzed the data and was responsible for GPS was asked several times at the seminar whether he synchronized the clock with the satellite and what was the frequency of the synchronization. He answered absolutely logical and numbers that recently, few milliseconds and so on and so on. So he answered something very, it sounds to people very logical, to specialists, to neuro specialists, very logical. But recently it turned out that it was just wrong. So even no explanatory responsiveness will help you to figure out what's going on if you cannot trust to who you ask. And also some philosophers argue that in order to get reliable answers in such a discussion, you need to be an authority. Definitely, the collaboration members were not authority for this data analysis. That's what's it about. So, and my summary slides, I am almost on time. So, still, this example reveals that what Lillian Huddison in her book about Fermilab called the controversy between the interests of lone independent researcher and the team character of work in big science. This controversy is still unresolved. This is still the same. The team works on the entire experiment, but individual researchers still need to be lone independent researchers in the sense as Bob Wilson, founder of this lab, Bob Wilson, suggested.
But could you say, maybe in more details, what is a controversy? Controversy.
Like a contradiction.
Contradiction in what? What is a contradiction between lone independent
between what you want to discover something yourself on one side, and you need to share with hundreds of people on the other hand. That's what it's about. So again, this explanatory responsiveness implies trust. So without trust, no responsiveness will help. Just okay. And again, the participation of the entire collaboration and external experts in data analysis and deliberations, which are necessary. First of all, Why is it good? First of all are more competent than general public, because almost all of them are physicists or PhD physicists, so they are just competent. Second, this makes aggregation more error-proof, because of what I said, that A knows P1 and P2 and P3, B knows P1, P2 and P3. Then, if somebody knows that not P2, we need to sort of discuss this, also reconsider, remeasure, so and scrutinize, in a sense. And if only A knows that P1 and B knows that P2, any single member, any single claim is a weak chain.
Yes. It happens.
And in this case, when out of 200 people, only one knew what he actually did in data, what he actually measured, that thing was broken. And also, this involvement of a community at large is a requirement of an epistemic justice, which I discussed it at the previous talk. I won't be repeating this, but this, again, it's not just an ethical claim, because if I just tell you yes, we need a justice, you can disagree with me, for example, because justice is not for everyone. It is a value. Some people value convenience, for example, much higher than justice if it is just something is convenient for them. Just I don't care for justice. My claim is not just that justice is good or equality in access to data, I mean collaboration, that it is good just because it is. No. Because only this equal access to data of all collaborators creates the situation of dissent, possible dissent, disagreement, and possible deliberations, which is more complicated than this, just hierarchical organization, more complex to realize. But nevertheless, it creates the situation of possible cross-check of each other, and everyone knows this and this and this, and after that we can cross-check and deliberate. And this is, on the other hand, such involvement of the entire collaboration, or maybe other members of other collaborations, to such sort of deliberations, is also a way, a first step to CBPR, or also a CBPR itself, because a large collaboration is not only a research group, it is a sort of small community. And this, in this sense, this is also a community-based participatory research. That's all what I wanted to say today.
Thanks.
Thank you very much for coming.